Welcome back. Let's learn about vectors. All right, so the first big topic that you'll learn about in Calculus 3 is the idea of vectors, or more specifically, vector quantities. But before we can talk about what vector quantities are, we first need to talk about scalar quantities. And scalar quantities, although the name may be new to you, they're actually something that you are very familiar with. Scalar quantities are just quantities that involve a single real number with some units. All right, so this is a lot of the quantities that you have worked with in math up to this point. So for example, that could be area, where a measurement could be 10 meters squared. It could be volume, where a measurement would be 100 feet cubed. It could be mass, where we'd have a measurement of maybe 8 grams. Or it could be time, where we have a measurement of 60 seconds. And I guess that would also be 1 minute. Or it could be temperature, where we could have a measurement like 70 degrees Celsius, or you could also measure that in Fahrenheit. Okay, but no matter the units, all of these are examples of scalar quantities. They involve one single real number and then some units, right? We had 10 meters squared, 100 feet cubed, 8 grams, a single real number with some units. And we call that single real number attached to those units for these scalar quantities, we call that number a scalar. Okay, so the terminology may be new, but the concept of a scalar really isn't all that new. When you hear the word scalar, just think of a constant real number. But as you might have guessed, not all quantities can be described by just one real number and some units. Some quantities are going to require a bit more information. Specifically, I'm referring to quantities that will require both a real number and a direction, such as with objects in motion. And this really becomes important later on in Calculus 3 when we begin to work in three-dimensional space. And we're not quite there yet, but even in 2 dimensions, sometimes quantities require both a value and a direction. All right, so for example, if you think about it, if you were traveling in a car and someone asks you how you got to your destination, you couldn't just give them a speed, right? You couldn't just say, I was traveling 40 miles per hour. That certainly tells somebody how fast you were going, but it doesn't tell them where you were headed. Were you driving 40 miles per hour north? Were you traveling south, east, west, northwest, southeast, right? Which way were you going? And so to more accurately describe where you were traveling, you not only want to include that speed of 40 miles per hour, you also want to include a direction. And so this idea of a quantity needing both a value, which we're going to call magnitude, more on that later, but the idea of a quantity needing both a magnitude and a direction leads to the concept of vectors and vector quantities. And so unlike scalar quantities, vector quantities are non-scalar quantities and require both a real number and a direction. And so some examples of vector quantities could be quantities of displacement or velocity, right? So for example, for displacement, a quantity could be that you walked 10 meters south, and a quantity for velocity could be maybe that you walked 5 miles per hour south. All right, so quantities for both displacement and velocity generally are going to require both a real number and a direction. All right, so that's the basic idea behind a vector quantity, but what exactly is a vector? Well, to put it simply, vectors are line segments that have a direction, or you might also refer to them as directed line segments. They're just line segments that have a direction. So for example, here we have 2 points, point A and point B. We could draw a vector between these 2 points by starting at point A and moving towards point B. All right, so I'll do that here. I'm going to draw a line between point A and point B. And since I started at point A and went towards point B, I'm going to indicate that direction by drawing a little arrow on the end of this line segment. So now it's no longer just a line segment, it's a directed line segment or a vector. All right, and there's a couple different ways that we could represent this vector that we've just drawn. One way is to just simply give the whole vector a letter to represent it. So for example, I'm going to represent this vector with V. But that's not the only thing that we're going to include in this notation to actually denote that this represents a vector, we're going to add this little special vector notation. I'm going to draw a half arrow above that letter V. So now what we have right here is the official vector notation. I have now labeled this vector right here as vector V. All right, now this might look a little bit different in a textbook. Typically, textbooks don't use this half arrow notation. Instead, they will just make the letter representing the vector bold. That's not something that we can really do when we handwrite this stuff. You can't easily make your handwriting bold. So instead, to avoid any confusion, we use this half arrow notation, which we call vector notation, and draw that above our letter. But now this is only one way to represent this vector. It is the most common way, but another way that we could represent it is by using these 2 points that the vector is connecting, point A and point B. Now these 2 points actually have names. Point A we call the initial point, and point B we call the terminal point. Now the reason they have these names is because point A is where the vector started, so it's where the vector initially begins, so point A is the initial point, and point B is where the vector is headed or where it ends, so it's the terminal point. It is where the vector terminates, essentially. All right, and so by using the initial point and the terminal point, we could also represent our vector, vector V, with this notation. We could start by writing the letter of the initial point, which is A, and then writing the letter of the terminal point, which is B, and then using that little half arrow notation above those 2 letters. And now what we have is vector AB. All right, and vector AB is the same as vector V. These are 2 ways to represent the same vector. Okay, and so vectors like vector V right here represent vector quantities. They have both a magnitude and a direction. But now practically, the magnitude part of that vector quantity is going to be the length of our vector. All right, so vector V here has a magnitude and a direction, where the magnitude is the length of the vector, and the direction could be described by either the slope of this line segment or the angle from an axis. And we'll work with angles and vectors in a later lesson. But for now, what you should know is that vectors like vector V have both a magnitude, which is their length, and a direction. Okay, so those are the very basics of what vectors are and what they look like. But when we actually work with vectors in Calculus 3, we're not going to be working with them in blank space like we did right here. Instead, we are going to work with vectors in a coordinate plane. Okay, so here we have a very simple coordinate plane, and if we want to draw a vector within this plane, we should choose an initial point and a terminal point. So I'm going to draw an initial point right here, and I'm going to label that with A, and then I'll draw a terminal point at this point right here, and I'll label that with B. So now if I want to draw a vector, what I can do is connect these 2 points, and then since I started at point A, the initial point, and ended at point B, the terminal point, I want to indicate that direction for my vector with an arrow. And then what I want to do is label my vector. Now I could go ahead and just label it as vector AB, but I'm going to add an additional notation of this vector being vector V. So we have V with this vector notation. Okay, so once again, this vector that I have drawn here could be represented by this notation, but it would be equivalent to writing it like this, where we have our initial point A, our terminal point B, and then that little half arrow above both of those points. All right, so these 2 notations represent the same vector that we have drawn in our coordinate plane. Now, let's get a little bit more specific. Let's write out what the actual values or the actual points are for our initial and terminal point. Now that they are within a coordinate system, right, we can write out a little bit more information now. We know more than just A is the initial point and B is the terminal point. Now we can actually say what those points are in our coordinate system. So let's start with the initial point, which I'm going to label with IP. Our initial point is point A, and point A is located at 1, 2. 1 is the x coordinate, and 2 is the y coordinate. So A is at point 1, 2. All right, now for our terminal point, which I'll label with TP, that is point B, and point B is located at 3, 3, right? The x value is 3, and the y value is also 3. So our terminal point is b, which is 3, 3. Okay, so now we know where this vector begins and ends, but now something else that we might want to know about this vector is its magnitude, right? What is the magnitude or the length of this vector? Now, before we talk about how to find that length or how to find that magnitude, first let's talk about the notation. If you want to represent the magnitude or the length of a vector, what you do is you take your vector notation. So for example, let's write vector v. You take that notation and then you just put 2 lines on either side of that notation. So like this, I'll draw 2 lines here and 2 lines here, before the vector notation and after. And when you have these double lines surrounding your vector, this now represents the magnitude or the length of that vector. And so you could also write it this way. This would be the same as having double lines around A and B with that vector notation. And so this would also represent the magnitude or the length of this vector, since it could also be represented by that vector notation. Okay, so that's how we denote the magnitude or denote the length, but how do we actually calculate it? How do we find the value of that magnitude? Well, if you think about what the length of this vector would actually be, or what it represents, this vector is just a directed line segment between 2 points, right? It starts at point A and ends at point B. And so the length of that vector would just be the distance between point A and point B. And if you remember from algebra, we can calculate the distance between 2 points using something called the distance formula. And the distance formula looks something like this. The distance is equal to the square root of the difference of our x values squared added to the difference of the y values squared. Now this formula is ultimately a result of the Pythagorean theorem, and that's something that you'll learn in algebra. So I'm not going to go too far into the origins of this formula here, but this is how you would calculate the distance between 2 points. Our first point is represented by x1, y1, that would be our initial point, and our second point, the terminal point, would be represented by x2, y2. So if we want to calculate the magnitude of our vector here, what we can do is take the square root of the difference of the x values between our terminal point and initial point, and then square them, and then add that to the difference in the y values for the terminal point and the initial point, and square them as well. So here's what that will look like. Let's start with the difference of the x values. Remember that you want to start with the terminal point. So we'll have 3 minus 1. The x value of the terminal point is 3, and the x value of the initial point is 1. So we'll have 3 minus 1 squared, and then we will add that to the difference in the y values. Once again, we're going to start with the terminal point because that is the second point. We always start with the y or x value from the second point first, and so we'll have 3 minus 2. All right, so if I write that in here, we'll have 3 minus 2 squared. All right, now if we simplify, this will be equal to the square root of 2 squared plus 1 squared. And 2 squared is 4, and 1 squared is 1. So this is equal to the square root of 4 plus 1, which is equal to the square root of 5. Okay, and so by using the distance formula, we are now able to calculate the length or the magnitude of this vector, vector v. The length of our vector is the square root of 5. But now let's draw a second vector in this coordinate plane. For this vector, I'm going to draw the initial point at the origin, so at the point 0, 0, and I'm going to label that with C. And then for the terminal point, I'm going to put that right here and label that with D. And then if I connect these 2 points, remembering that C is the initial point and D is the terminal point, then I'll draw the arrow in this direction, and I'll label this vector as vector W. So we have W, and then that little half arrow above it to denote that this is a vector. So this vector would be represented by this notation, or you could also represent it like this. We could have C, and then D, and then the vector notation. So both of these notations would accurately represent this new vector that I just drew. Now for this vector, the initial point is just the origin, and it's point C. So we have 0, 0. And the terminal point is point D, which is located at 2, 1. 2 is the x value and 1 is the y value. So we have 2, 1. All right, and now if we want to calculate the magnitude of vector w, we could do the same thing that we did for vector v. We'll use the distance formula and take the square root of the difference of the x value squared plus the difference of the y value squared for the terminal and initial point. So we'll have the square root of 2 minus 0 squared. So we'll have 2 minus 0 squared plus 1 minus 0 squared. So we'll have 1 minus 0 squared. Now this will just simplify to the square root of 2 squared plus 1 squared, which looks pretty familiar, right? That's the same result we had for this vector. 2 squared is 4, 1 squared is 1, 4 plus 1 is 5. So the magnitude, or the length, of vector w is also the square root of 5. And so that's pretty interesting. Both of these vectors that I drew have the same magnitude, or they have the same length. And so it might seem like these two vectors are similar in some way, or they're related in some way. And so that's interesting, but let's take a look at their direction as well. And the way that we can do that is by looking at the slope of each of these vectors. And so if you remember from algebra, once again, we know that slope is equal to the difference in the y values divided by the difference in the x values, right? We have rise over run. Now we could go through and actually calculate this for both of these vectors using the x and y values for their initial and terminal points, but to make it a little bit easier on ourselves, since we have a nice graph here, we can just visually find the slope by counting the rise over run, right? So for vector v, our rise, or the change in y values, is just 1. We went from 2 to 3. And then the change in the x values, or the run, will be 1, 2. Right? We moved from x equals 1 to x equals 3. So the slope for vector v is going to be equal to 1 over 2, or 1/2. And if we do the same thing for vector w, we also move up 1 in the y direction and then over 2 in the x direction. So we have 1 over 2 for the slope of w. So the slope is equal to 1/2, which is the same slope. Both of these two vectors that we have here, vector v and vector w, have the same magnitude and the same slope. And this is a very important point about vectors. When two vectors have the same magnitude and the same slope, or the same direction, then we can conclude that those vectors are what we call equivalent vectors. So we would say that vector v and vector w are equivalent. They have the same magnitude and they have the same direction. The only difference between the two vectors is where they are positioned within the coordinate plane. And this is a nice way to introduce you to the next concept we're going to talk about, which are position vectors. All right, so if you look at this graph here that we were just working with, vector w here is actually a vector that we would say is in standard position. And the reason we say that is because its initial point is at the origin, the point 0, 0. And so since that vector is in the standard position, we would call it a position vector. And so in general, a vector v with an initial point at the origin and a terminal point at some point where you have an x-coordinate and a y-coordinate represented by v1 and v2, that is called a position vector of that point at v1, v2. All right, so if we just draw a vector here where the initial point is at the origin and it ends at some other terminal point right here that we would call P of v1, v2, if this is vector v, then this vector, vector v, is a position vector. All right, and we actually have a special notation for position vectors, as they're going to be the most common type of vector we work with in Calculus 3, and it looks like this. We represent that position vector v with this notation where we have these angle brackets around the x and y coordinate of that terminal point. All right, and it's important that when you write out this notation for a position vector, that you write these angled brackets. If you write it like this with the open curved brackets, this does not represent a vector. This represents a point at this xy coordinate. All right, this does not represent a vector, this does. you need the angled brackets. That is how we differentiate between a position vector and a coordinate point, so you need to make sure to use the correct notation when working with vectors and points. All right, now another way that you'll hear this called is component form. That's what this notation will be referred to sometimes. We call it component form because the coordinates of that terminal point would be the components of the vector. We have v1 and v2, which represent the x-coordinate and the y-coordinate, which are the two components of that position vector. Okay, now a couple things to note about position vectors. If both the initial point and the terminal point are the origin, if they're both the point 0, 0, then we call that vector the zero vector, and we represent the zero vector with a special notation that looks like this. We have 0, and then the vector notation, and that's equal to the vector 0, 0. All right, that's the component form of the zero vector. This doesn't really look like anything if you were to graph it. It's simply just going to be a point at the origin because both the initial and terminal points are the origin. And so the zero vector doesn't really look like anything more than just a point. Okay, now another thing to mention is that if the components of two vectors in component form, or two position vectors, if their components are equal, then those vectors are also equal. They're the same vector. So for example, if we had a vector v that was denoted by this, if we had a vector of 3, 5, and then we had a second vector, let's say vector w instead of v, and that's also equal to 3, 5, these are both vectors that are position vectors of the point 3, 5. They are both vectors that start at the origin and have a terminal point of 3, 5. And so since their components are equal, the x components are the same and the y components are the same, we would say that those vectors are equal. They are the same. So we could write an equal sign between those two vectors. They're the same thing. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. All right, now for any vector, we can actually determine its component form and turn it into a position vector. And so let me show you what I mean. If we look at our graph from earlier, this is the graph where we had our equivalent vectors, vector v and vector w. Vector w is already a position vector, as we discussed earlier. Its initial point is at the origin, but vector v is not a position vector. But we can turn it into a position vector, or in other words, find its component form. And so here's how we can do that. Remember that for vector v, the initial point is a, which is 1, 2. That's this point right here, 1, 2. And the terminal point was point B, which is at the point 3, 3. So we have 3, 3. We can find the position vector for vector v by simply taking the difference of the x-coordinates and the y-coordinates of the terminal and initial point. All right, and so here's what that looks like. Vector v's component form will look like this. We'll have the difference of our x values. So we'll have 3 minus 1, and then we'll have the difference of our y values. So we'll have 3 minus 2. Okay, and then if we simplify, 3 minus 1 is 2, and 3 minus 2 is 1. So the component form of vector v is 2, 1. And so now vector v is a position vector, and it's going to be the same exact vector as vector w. Right, this vector is the position vector for the point 2, 1, which is this point right here, 2, 1. So vector w is the position vector for vector v that we just found. Okay, so in general, if you have a vector, vector v, that has an initial point of a, and that point has an x and y coordinate of a1, a2, and then a terminal point of b, which has an x and y coordinate of b1 comma b2, then the component form of vector v will be equal to the difference of the x values for the terminal and initial point. So we'll have b1 minus a1, and then the difference of the y values for the terminal and initial point. So we'll have b2 minus a2. And that will be the component form of vector v. Now, of course, we could then also write it like this. The component form of vector v would have the components of v1 comma v2. And that would also represent the component form of vector v. v1 minus a1 becomes v1, b2 minus a2 becomes v2, where v1 and v2 are the components of the position vector v. Okay, now if we wanted to calculate the magnitude of our position vector, it actually becomes a little bit easier than it was before when we were only working with initial points and terminal points, right? Remember that we were using the distance formula where we had the differences of our x and y coordinates, but we were taking the square root of the sum of those differences squared. All right, and so since those differences just become v1 and v2, we can find the magnitude of a position vector, or a vector in component form, by just taking the square root of the sum of our components squared. And that looks like this. For a position vector v with components v1 and v2, the magnitude of that vector is just equal to the square root of v1 squared plus v2 squared. Okay, and just note that when you're working with position vectors, sometimes that magnitude or that length will be called the norm of v. I won't really use that terminology too much, but that is another way that you might see the magnitude or the length referred to. Okay, and a couple other things to note about magnitude is if the magnitude of a vector is equal to 0, that vector is the 0 vector. It has a component form of 0, 0. And if the magnitude of a vector is equal to 1, then that vector is a unit vector. And we'll talk more about unit vectors in a future lesson. Okay, but with that, before we close out this lesson, let's look at one example problem that is going to put everything together that we talked about in this video. Okay, so here we have an example problem. We want to find the component form and length, which is the magnitude, of the vector v that has initial point 3, negative 8 and terminal point negative 2, 6. All right, so the first thing that we should do here is draw this vector. We should draw out our coordinate plane, plot the initial and terminal point, and see what our vector looks like. So let's do that. I'm going to draw the y-axis, and then I'll draw the x-axis. And let's label them. This is our x-axis, and this is our y-axis. And I'm going to say that this is x equals 2, x equals 4, and x equals 6. And then this is y equals 2, y equals 4, y equals 6. And then we have x equals negative 2, x equals negative 4, x equals negative 6, and then y equals negative 2, y equals negative 4, and y equals negative 6. All right, so now let's plot the initial point and terminal point. I'm going to plot the initial point with this color, and then plot the terminal point with this color. So 3, negative 8 takes us to 1, 2, 3, and then we need to go down to negative 8. So let me extend the y-axis here. We need to go a little bit lower. And so we'll say that this right here is negative 8. And so 3, negative 8 will be right here. And so that's our initial point. I'm actually going to label that with A. And so I'm just going to put A right there. And then B will be our terminal point. So I'll label this with B. And that is at negative 2, 6. So if we go to our coordinate plane, negative 2, 6 is right here. So that is our terminal point B. Okay, so now what we should do is connect these 2 points. We should start at our initial point and connect it to the terminal point to create our vector. So I'm going to do that like this. That is our vector that I'm going to label with V. So that's our vector V. And now what we want to do is find the component form of that vector. We want to put that vector in the standard position where the terminal point is at the origin so that it is a position vector. All right, and so in order to do that, to find the component form of vector v, what we need to do is take the difference of the x values and then take the difference of the y values. And remember, you use the x and y values for the terminal point first, and then you use the values for the initial point. All right, so for the x values, we have negative 2 minus 3, right? Negative 2 minus 3. And then for the y values, we have 6 minus negative 8. So 6 minus negative 8. Okay, so now if we simplify, we'll have the component form of vector v. Now negative 2 minus 3 is negative 5, and 6 minus negative 8, that's the same as 6 plus 8. Those negatives cancel out, and 6 plus 8 is 14. So the component form of vector v will be negative 5, comma 14. Okay, so that's the solution to part of our problem. We found the component form of vector v. Now what we want to do is find the length, or the magnitude. And that's going to be pretty easy now that we know the component form of vector v. The magnitude of vector v will be equal to the square root of the sum of the components squared. So we'll have negative 5 squared plus 14 squared. Now, negative 5 squared is 25, so this is equal to the square root of 25 plus 14 squared, which is 196, and 25 plus 196 is 221, and so this is equal to the square root of 221, which I believe does not simplify any further. And so the square root of 221 is the length or the magnitude of vector v. Okay, so now we have completely solved this example. And just note that if you wanted to, you could also graph this position vector. Vector v is the position vector of the point negative 5, 14. So if we extended this coordinate system, we could go to negative 1, negative 2, negative 3, negative 4, negative 5, and then up 14 in the positive y direction. And then we would have our position vector that starts at the origin and ends at that terminal point of negative 5, 14. Okay, so if you wanted to do that, if you wanted to graph that position vector, you could, but we didn't really need to for this example. We just wanted to find the component form and the magnitude or the length of that vector. Okay, so hopefully this example helped you to bring everything together that we talked about in this video. But if you want to work through some more examples and get more familiar with vectors, feel free to check out my examples video for this topic that I'll have linked here on the screen. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.